Let me now showcase typical applications of Lagrangian methods. What are typical applications for particle simulations, you might ask? Well, one of which is mixing of particles in process equipment. So what you see here on the top left is the velocity distribution of individual particles in an extruder. An extruder is a device that consists of a barrel and an extruder screw that's shown here. And this is the top view essentially. And here the particles that were colored with velocity, you see there is a big velocity change in this small gap between the barrel and the screw. And on the bottom here we have the particles colored by their essentially concentration, for example. If particles have a concentration of material A or B, right? And what you can then do is you can then simulate the particle motion and study how well the particles are mixing in the equipment. Another important example is hopper discharge. So here you see a simplified hopper with tablet-shaped particles. We have an opening here. Particles are colored here simply by the ID. The ID is nothing else as here, essentially the set position. And again, we can study how well the particle mix upon hopper discharge. And this is important for many applications. Imagine, for example, we are discharging a material with different composition, and it is of big importance how the particles discharge and which particles exit first this hopper or are retained in the hopper. Other applications of Lagrangian methods for fluids, for example, include the so-called smoothed particle hydrodynamics calculation or simulation. Here you see a fluid flow with a free interface. So here we have a fluid, here we have a very low density fluid, for example, air. Here you see the density distribution. So in these methods, the SPH method, we track the particle positions and also reconstruct the local density of the fluid, which you see is around 1000, so this is water. What I would like to show you now is how such a SPH type of simulation looks like. Here you see this dam break example, which is an archetypal example of such an SPH type. First, let us look at the situation at low viscosity. You see here the fluid is splashing at the other corner of the box and flowing back and forth, as you would expect for a low viscosity fluid. You see here these nice waves as they propagate. And this is important, for example, for coastal engineering. As you might imagine, you can use this kind of simulations to study, for example, forces on obstacles at the coast. We can now increase the viscosity of the fluid and see what's happening. Not a lot of things change if you make it a little bit more viscous, but we can go to ultra viscous, for example, here, and then you really see the power of these methods. You can then predict what happens if you change the viscosity of your fluid significantly. You see there's no splashing, there is no wave formation essentially, and it looks much, much different. Let us also now consider an example where we track atoms in a Lagrangian method. You will see more examples in a minute. Here, for example, we showcase the stretching, the deformation, mechanical deformation of a polymeric material. You can see it that clearly, but the small dots are here the atoms that you track, and the lines between them are the chemical bonds that you also simulate with such a MD simulation, as they are called. Let us next look at the industrial impact of such simulations. What are real-world challenges that are addressed by such simulations? First, start with MD simulations, a very important class of Lagrangian methods similar to the discrete element method. These methods, these MD methods, are used for prediction of diffusion rates, for example, in materials, also under extreme conditions. You see here a simulation of Philipp Rosenauer from TU Graz that is interested, for example, in the diffusion of water molecules in polymeric materials. Water is here shown as the yellow small molecules, and these molecules then diffuse into pores of polymers, for example. The polymer is here, this big structure here, this red, blue, gray, white colored atoms and molecules. And these are very, very important simulations that help people in industry designing, for example, better molecules for polymers. Let's now focus on a classical DEM simulation. Here, for example, we have simulated the birth of particles. So how particles are born, for example, when we synthesize them in a reactor. Here we synthesize, for example, a polymer. And here you see how such a polymer grain is growing. These grains are tiny initially, but then they kind of pop like popcorn. And depending on the local availability of a monomer, the structure of the final polymer particle can be different. So you see here that the DEM can also be used to model particles that grow during the simulation time. So this is another important thing that you should know, that the particles not necessarily have to have a constant size, but they can also grow, for example, during the simulation, because, for example, they absorb material from the ambient fluid. Another real-world challenge that can be addressed with DEM simulations is the performance of reactors. And here we're talking about chemical reactors. What you will see next are CFD DEM simulations, so combined computational fluid dynamics, discrete element method based simulations of mixing in such a chemical reactor. Here we track the motion of particles with the DEM. The particles are quite small, you can hardly see them. Plus, we also simulate the velocity pressure distribution in the fluid. The fluid is here not shown. What is shown here is the concentration of the educt, chemical reacting species, that is adsorbing to the surface of the particles. So when we simulate these reactors for fast reactions, you see we have a very inhomogeneous mixing of this reactive species that comes from the fluid phase. And in other words, it's a bad assumption to say the gas is well mixed in this reactor. In contrast, if the reaction is slow, then we have a relatively uniform distribution. The gas can come everywhere and all the particles can participate in the chemical reaction. For example, in a catalytic reaction to convert hydrocarbons. Another real-world application are fixed bed reactors. Fixed bed reactors are important for the chemical industry, and here the main interest of those industrial partners is in creating precise digital twins. For example, to better control a process. What you see here are simulations of heat transfer from such particles in a fixed bed reactor with very accurate CFD simulations. We call them particle resolved, PR, direct numerical simulations, where the particle positions have been found initially by doing a DEM simulation. We can subsequently analyze those simulation results and build better models that can then be used by industrial partners, for example, to predict what's going on in their reactors to better control their process.